This time, we are going to show the kernel and the nullity of a linear transformation involving matrices here. We have two matrices of 2 by 2 matrices. Then we're going to show the kernel, which means the set of all vectors that could result to a zero vector, and the nullity, which is related to our kernel. Now, take note that this involves matrices, so we are going to also use the concept of this. Okay, the transformation of the vector v is equal to the matrix A times v, which is also equal to the zero vector. Since we are on R2 or a 2 by 2 matrix, our zero vector is at 0, 0, and the vector v that we're going to solve is actually maybe represented as v sub 1 and v sub 2. So we're going to solve for all possible values of the vector v here, which means all possible values of v sub 1 and v sub 2, and with that it would become part of a kernel. The nullity, on the other hand, is the dimension of the basis of the kernel. So we're going to determine later the dimension of the basis of the kernel once we are done with the kernel. So to do this, we will be using this later. The technique here is from this matrix, we are going to come up with its row echelon form, or even the reduced row echelon form if you can. And of course, the row echelon form will also give us the result. So not to make this video longer, let's make the let's copy this negative 1, 1, 1, and 1, and come up with the row echelon form. We can interchange here row 1 and row 2, so that our row 1 will become positive 1 and row 2 will be negative 1, or you can multiply row 1 by negative 1, but in this case I'm just going to interchange them. The next here is to make this 0. Okay, but making that 0, we just simply need to add row 1 and row 2 to have a new row 2. So we have here 1, 1, this would become 0, this would become 2, because 1 plus negative 1 is 0, 1 plus 1 is 2. Here, let's multiply 1/2 to row 2 for a new row 2. In short, the form in row echelon form is 1, 1, 0, and 1. Of course, we can still move further and solve for this, making it a reduced row echelon form. But with this already, we can now multiply this to our v sub 1 and v sub 2, because this is what it meant. A times v must be equal to the zero vector in R2. So we have two equations here. We have the v sub 1 plus v sub 2 being 0, and v sub 2 being 0 already. Again, this is just one of the possible steps. You could always come up with the reduced row echelon form of this so that you get the exact value automatically. But since I have here this v sub 2 being 0, using this, you have v sub 1 plus 0 be 0. V sub 1 is also 0. In short, okay, the vector for this matrix that will allow this to become equal to the zero vector is the zero vector itself. In short, the kernel of T is just the set containing the zero vector itself. Okay, that's the kernel of T for our first matrix. Now, the nullity of T, again, is the dimension of the basis. Okay, so looking at here, we have the nullity of T. We have here the dimension of the basis. We only have one element here. However, when we talk about dimension, we are going to exclude counting the zero vector itself. Even if this set contains one element, which is zero vector, the nullity of T, which is the dimension of your kernel, or the dimension of the basis of your kernel, doesn't count the zero vector. In short, the nullity of T for this matrix is 0. So again, this only happens if the vector that is part of the kernel of T is just the zero vector itself. Okay, let's duplicate the same process here. Let's come up with the row echelon form of this set, matrix. We have negative 6 here. So what we could do here is we can multiply 1/3 for our row 1, okay, to have a new row 1, so that this would be a leading 1. We have 1, of course this is a 2/3, okay, this is still negative 9, this is negative 6. And then to make this 0, we'll be multiplying 9 to row 1 plus row 2 for a new row 2. So we have here 1 and 2/3 still. 9 times 1 is 9 plus negative 9, 0. 9 times 2/3, that's 3 times 2, 6. Minus 6, 0 here. Once we reach this item, this is already a row echelon form. Let's multiply now v sub 1 and v sub 2, and this should be equated to the 0 vector again here. So we only have one equation here, v sub 1 plus 2/3 of v sub 2 be equal to 0. We have two variables on one equation. This would mean we can let one of the two, specifically v sub 2, be an arbitrary constant t. In this case, this would become v sub 1 plus 2/3 of t equal to 0. So v sub 1 is equal to negative 2/3 of t. Our vector here is a vector on R2 with the first component negative 2/3 of t, and our second is actually t. But let me make it better in the form of a set so that we could have our kernel here. The kernel of t is a set containing, now factoring t, negative 2/3 and 1, such that t is an element of R. So this would be our kernel. We have one vector, and all of its multiples could make this matrix be equal to the 0 vector. This is the kernel of t. However, the nullity of t will talk about the dimension of the basis of the kernel. We only count this as 1. In short, the nullity of t here is just 1, meaning there's only one specific vector and just multiples of it that come out that could result for the matrix to become a 0 vector. So we have only one for this kernel of t. So this is how we show the kernel and nullity of a linear transformation for a 2 by 2 matrix here. Thank you very much for watching.